next up, we have a first-time DConf speaker. Yeah, we like first-time speakers, and this is going to be an interesting topic by the sounds of things. So, Tom, please take it away.
So, as Ethan said, I'm Tom. I'm from imec, and the question that we want to answer today is like, can we use D for HPC, aka high-performance computing? Is D ready to be used for supercomputers? Overview of the talk. I'll start by explaining why it's so hard to get good efficiency, good use out of supercomputers, why people spend so much effort. And then what we propose as a better way to program supercomputers is using tasks all the way down, task level parallelism all the way down. And we actually have an implementation that combines the high-level power of D and the metaprogramming in D with a low-level software stack in C sitting on FreeRTOS, such that you can efficiently use supercomputers. To put the thing into perspective, I'll talk about our own supercomputing architecture and why this implementation and how this implementation is actually tailored to this kind of supercomputer architectures. And then finally, I'll come to the most interesting part, I think, for the talk for you guys is like what we as a HPC lab think about using D for supercomputing and what are the joys and what are the pains of using D for HPC. I'm from imec. imec is a research institute in Belgium. We have about 5,000 people, and we have a big, shiny factory there, which cost about 4 billion euros to build. And what we do there is we make chips. We spend most of the money on actually making new transistors. So what am I as a software guy doing at imec? Well, actually, we also have a big group, about 50 to 60 people working on hardware, software co-design. We have many more people working on software, but the group I'm in is working on hardware, software co-design. So what we do there is we make better software to use better hardware, and we make sure that we add the right computer architecture components to the hardware such that the software can run better on it. And we adapt the software to actually then use these better computer architecture features. Hopefully this will become better as we become clearer as we go through the talk, right? So in a specific application domain we're focusing on that we build computer architecture solutions for is high-performance computing, and more specifically is about large engineering simulations. So what I mean by engineering simulations, these are things like fluid dynamics, like the aerodynamics of an airplane wing, car crash simulations. We have a project together with a large software company who have software to do car crash simulations, chemistry, combustion engines. All of these simulations, they require large computers. They require the use of very optimized hardware and optimized software. So this is a list of the top 5 fastest supercomputers of this year. They make this list twice a year. This is the list from June 2024. You see that these computers have millions of cores, and they can do quintillion operations per second. So for example, 1 exaflop, the top computer there, 1 exaflop, if you let all the people on the planet do 1 calculation per second in parallel, it would still take 4,000 years for all those people to do the same calculation as what this computer can do in a single second, right? So that's a lot of compute power. But these engineering simulations, when you look at, a typical benchmark that is used to represent the type of workload for these engineering simulations is called HPCG. And if you run this HPCG benchmark on those top supercomputers, you see in the last column that actually that benchmark only uses 1% of the peak performance of that computer. And part of it is because it's very difficult to get a good performance for these types of simulations from that supercomputer, right? So how can we make it better? How can we make it in such a way that that we can get better performance for those type of engineering simulations? Part of the problem comes from the fact that today's high-performance computers are very heterogeneous. They have many different levels. For example, it starts at the lowest level where you have a single core that can execute vector instructions. And then, but you don't have a single core. You have multiple cores inside the server, and those multiple cores, they share the same memory, so they talk to each other through shared memory parallelism. You have multiple servers connected in a rack. The servers in the rack talk to each other using one type of networking infrastructure, and they have multiple racks. They talk to each other typically using a different type of networking. And you, as a programmer, typically what you have to do as a high-performance programming, you not only have to deal with the functionality, writing down what your simulation actually has to do, but you also have to map it to all those different levels. And for example, one of the most difficult things is making sure that the data is where the compute needs to be, right? You need to do a certain computation inside a thread, for example, and it can be that the data is at the total other end of the supercomputer. And of course, that's something you don't want, because waiting for the data takes an enormous amount of time in which you could do a lot more computation. So data movement, optimizing data movement is, for example, one of the key performance optimizations that people do. So, and then every time you go from, if you want to run a small problem, you probably want to run that small problem on a small machine, and then you scale up your problem because you, for example, you want to have a more refined view of your simulation, you want to scale it up. Every time you do that, it's going to cost you time and money, because every time you need to rethink about how am I going to use all of these different components. I have more cores, I have more memory. If I go to a bigger system, so I need to change my parallelization and I need to change my data distribution. What we want to do is we want to decouple these two things. We want to decouple the fact that the programmer should only worry about functionality and should expose as much parallelism as possible. And then at the other side, we have the runtime. This is an intelligent runtime that the programmer that is writing the engineering simulation doesn't have to write itself. That the runtime is dealing about scheduling, like what task, what piece of code to execute on what core, on what machine. The data distribution, what data do I store where, when do I move data from here to there, and the load balancing. And by decoupling the two, it should be much easier to scale out your simulation, because you don't have to change the functionality, because the fact that you're moving to a larger computer is all handled by the runtime. The main building block to achieve better scaling, not having to change your program, is by using tasks everywhere. You decouple your program into small tasks. A task is the smallest unit of compute. A task is executable, and if you have multiple tasks, these tasks can run in parallel and they can spawn new tasks. Whether tasks can run in parallel depends on dependencies. As a programmer, you need to write your program in terms of tasks with dependencies. And the two last bullet points, these are the most important properties to get good performance. And that is the fact that all the inputs of a task are read-only. You cannot modify the inputs of a task, whether the input of a task is a vector, is a scalar, a binary, a single element, or a large data structure, whether it has pointers. The input of a task is always read-only, which allows us to move. If data is needed by multiple tasks, we're free to make copies. Then we can reuse those copies on the whole machine. The output is write-only, and that also allows us that once the task is finished, the output is converted from write-only to read-only. This is a contrived example. You would never write this, the Fibonacci. You would never write this that way. But if you want to write Fibonacci in this paradigm, you would say, okay, the Fibonacci of 3, I decompose that into two tasks. One task is the Fibonacci of 2, which is then, of course, you define a task recursively by spawning this task of the same type, and the Fibonacci of 1. And then the third task is then adding those two together, because the Fibonacci of 3 is the Fibonacci of 1 plus the Fibonacci of 2. And then these blue dotted arrows, they say the dependencies. And then on the right-hand side, that's low-level code that actually creates those tasks by calling the lower-level primitives new task. But you would never actually have to write those low-level primitives because we have much higher-level primitives, such as map and reduce, and parallel data structures that allows you to write much higher-level primitives that generate those tasks for you. So tasks, the basic way to express your parallelism in this programming model. I will now talk how we actually implemented this task-based programming model by first explaining the high-level part written in D, like how you write your applications, this programming model is composable by integrating with libraries that are also written in terms of tasks, and then the standard library, and then the runtime that execute those tasks, the part in D and the part in C, until all the way to the lowest level where we run this on a real supercomputer, either a standard one or one that we have designed ourselves, where the task management is done on a very small RISC-V based processor. Later I will come like, okay, what is the power of D in actually being able to achieve all of that, and why we chose D. As I said, fundamental pattern, the basic thing that is underneath everything is these tasks. And this is another example where I show the same thing again, except it's more, well, it's something that you might really write. So you want to add two vectors, vector A plus vector B is vector C. What you would typically do is the same pattern again. If the length of the vector is below a certain threshold, the cutoff, you would call a kernel. The kernel can be something that is then executed on an accelerator, because in these supercomputers you typically have GPU-like accelerators. There are no supercomputers these days that don't have these, that don't have accelerators. They're not always GPUs. There can be other types of accelerators. But usually, almost always at the bottom you have accelerators. Otherwise, if you're above the threshold, you split up the task into smaller tasks, and then you combine the results of the smaller task into the bigger result for this main task. This slide also highlights the alternative syntax where we use a nicer syntax with EXO, which actually is a smaller version of creation of a new task. This is a template, so we can use templates instead of function pointers. Tasks have member functions, or we can use generic functions that allows us to say you first execute a sum task, and then you create another sum task, and only when those two have finished, that's the meaning of the then you can create the append rows task, which actually combines the sum task into the final result. So this allows us to not explicitly have to make these task dependencies, the blue dotted arrows. Those are automatically created using this syntax. And then if we can go even one level up, for example, we have defined a map and a reduce. This has the same semantics as the map and the reduce in the std parallelism, or the std parallel in the D runtime or in Phobos. Except, of course, that this is not implemented on a single machine with multiple cores. This is then implemented on a whole supercomputing using multiple machines. The data types, they're not regular vectors, but the vectors that you see in this slide are actually distributed vectors. And we can know where the data, the different pieces of the vector are, and how they're distributed on the supercomputer. But apart from that, the map and the reduce have the same semantics as the standard map and reduce. The difference is that they're running on the whole machine. And then you can go even one level up in the sense that we implemented a GPT, a large language model, that uses different types of libraries that operate on these distributed data types. For example, we have the basic, the fundamental operation in a large language model is a dot product or a matrix-matrix multiplication. On top of that, you use this matrix-matrix multiplication to compose the whole structure of your neural network. And underneath, all of this is decomposed into tasks. And this allows you to write very compactly, intuitively, almost the same way as you would write this in PyTorch, except that for this, PyTorch runs on a single node, a single machine, and this can then run on your whole supercomputer if you would want to. If you have enough tasks to fill your whole supercomputer. So now we covered the top level part. We covered the user application, the application high-level libraries like the matrix-matrix multiplication, linear algebra, We have explained tasks and map and reduce. Let's go down a bit, but let's make a detour to the hardware software co-design. So as I said, I'm part of a group that does hardware software co-design. So we not only make better software, we also design hardware. This slide is about an architecture that we designed for HPC and AI applications. So a hardware that can both do these engineering simulations, but also can support AI applications, because we see more and more engineering simulations also incorporating AI. And what we can do, or what the group then does, is like we evaluate quite a lot of different computer architectures for their performance and their cost. And that way we can say, okay, what is a good sweet spot in terms of performance and cost? What are architectures which are good? And most importantly, we focus on solving data movement bottlenecks. Because as I said, data movement, making sure that the data for the task is at the right time, at the right place, that's the key ingredient. When you look at the system architecture that we designed, most of the components in that architecture, all the light blue components in this architecture, what they are doing is they're accelerators. They're specially designed hardware to move the data, because moving data is the key component. And then the CCAs, as they're called, they're actually the compute engines. They are the number crunchers. They're the ones that do, for example, all the matrix multiplications. The other thing is in dark blue, the RTM. That's the runtime manager. That's actually the code that runs the code to create the task, to split up the task, and all of that. So all of the decode that I showed, except the kernels, that's running on this very tiny RTM runtime manager processor, which is a RISC-V-based processor. Most of the die area, most of the area on the chip is dedicated to actually data movement, right? So that's why we didn't run on this runtime manager, this RTM processor that's running all this decode. We chose to go to a BetterC implementation. We do not run on a standard Linux, for example, but we run on something that's called FreeRTOS. And FreeRTOS is a very lightweight, very small memory footprint operating system, which is especially designed to run on these small processors that do all the management. We have this top level of the software stack written in D, the lower level written in C, sitting on top of FreeRTOS running on your hardware. One of the things where D is very powerful is that we use templates and mix-ins to seamlessly translate or go from the D land to C land. So this is an example where you create a new task. A new task is a template which accepts a function, and the function is actually the code that you want to execute when you run this task. But in C land, the task is represented by a function pointer, and actually all the tasks in C land are having void pointer arguments. Before we go from D to C, we remove all of the type information, and then we come back up when the task is actually executed. We need to call a D function, but this D function doesn't accept void pointer arguments, so then we have another template which then again converts the C void pointer arguments to this task back to the correct types in D land. And for this, the static for each, the mix-ins, they work very well to make sure that the code not only works, but we also can do type checking when you call a task, that you actually call the task with the correct arguments. For example, this wrap function is then going when you go up from C land back to D land. The RTM processor is a very small processor, so that's why we chose to use BetterC. We don't want to take the whole D runtime onto this small processor. So we were very happy to use mix-in and templates, unit tests, imports. I mean, no C includes anymore, but imports. Array slicing still works, and some of the standard libraries also still works. There are some things that we had to leave behind, of course. Most of the standard library, no classes. That's something that we really would have liked to have classes, real classes in BetterC land, and no runtime type information, and no standard threading and synchronization. So FreeRTOS has an implementation of the things that we need. So FreeRTOS has semaphores, has threads, has malloc, has logging support. So we could write a layer in between D land and FreeRTOS that translates the things that we wanted to use in D to their FreeRTOS equivalent. We had to implement a dvec because we couldn't use the standard D arrays, right? But after all this work, we were very happy with the fact that the whole software stack running on this small processor, the binary was only 35 kilobytes. So we were able to reduce a statically stripped binary, everything included, this complete large code for this large language model, only 35 kilobytes on this RISC-V processor. When you run it on your laptop and you're not running it on, you can still run it on Linux using FreeRTOS or using standard Linux. The code size was a bit bigger, but still one of the things we wanted to achieve was small code size, and this is something that we did. So up to the final part of the presentation, the good, the bad, and the ugly of using D in this context. So I'll go in detail for each of the 3 different steps, and then I'll conclude by, okay, what does this mean for using D in this context? Can we use D? Is it a good idea for D? Will other people use D or not? Let's start with the good. D is a very powerful language if you know what you're doing. We were able to achieve a very small code footprint with BetterC. We used the LDC compiler to generate RISC-V code. It was no problem at all, especially the templates, the mixin, the reflection inside the templates. That was also very useful for us to be able to achieve all of this high-level code in a small code base. Some other things that we liked is this uniform function call syntax, scope cards. Those are all the things that we really liked. The other hand, D is not easy to learn. D has a relatively small user base. Every time we looked on Stack Overflow, or we Googled for something for dlang, Google was helpfully telling us, yeah, probably you mean Golang, eh? You're not looking for dlang? No, I don't know about that. Another thing that was not easy was the integration with C. It was not clear in the beginning to us what was included in BetterC and what not, why it was not there. We wrote manual declarations for the extern C functions that we were using in FreeRTOS. We looked a bit at using ImportC, DPP, not DTAP, DStep, C to D, H to D, but in the end, we didn't make a decision and we didn't use any of these automatic tools to expose C libraries in D. So that was working as expected, but not very well. We still have we had some issues there. And the other thing, which was something that puzzled us in the beginning, was the fact that all the variables are thread local by default. And if you want to have a shared variable between different D threads, then this shared would create a different type. If you add shared to a variable, this would be a different type than just a regular variable, and this would ripple through across many different functions, which was also something that we didn't want. So we ended up using, especially in the beginning, using __g shared for when we were doing prototyping in D, where we are not yet using the FreeRTOS backend. But in the end, once we understood all of these things, this also worked out. Some of the ugly things that we encountered, and integration with existing libraries at the bottom there, that I have a separate slide on. But the top thing is about dub. And we struggled quite a lot because we have a build system, standard build system with CMake. And we were trying to figure out how to integrate this build system with dub. And in the end, we used a very simple hack that we would call dub from within CMake, put all the decode that we had in a single library, and this dub command would simply generate the library. But as you see on the slide, this very long CMake command, it's not something which I think is a sustainable solution. I looked a bit at how there's an extension or a package to use D, to call the D compiler from CMake, or to have a better integration between CMake and D. But we didn't do much of the exploration there. The other thing that we had is that we had a lot of test cases. So we ended up writing a script that generates a dub to JSON for all of these test cases. So there we had a feeling that the dub was not powerful enough for the things that we wanted to do. So this morning I saw the talk about redub, and I saw and as mentioned reggae. So that's that's certainly one of the things we're going to check out, like whether that would be a better build system for this type of environments. And then the most problematic part for the moment is integration with existing libraries. So almost all of the programs in HPC, high performance computing, use MPI and use HDF5. MPI is a communication library, HDF5 is a file format with a library. For MPI, there were at least 3 different repos on GitHub, which each have their own MPI.d, which would each expose a different subset of MPI, because MPI is a very large library with many different functions for point-to-point communication, for all-to-all communication. But none of the packages using MPI were in our extent feature complete, or some of them were old and they didn't work with a newer version of MPI. So in the end, we didn't find a good way to have an MPI package for D. The second thing about HDF5, we put some effort in there, but we couldn't get it to work with the limited time that we spend in there. Probably by now we know more about D, we know more about how to integrate, we might be able to get it to work. But when we did this project, what we did is we wanted to read in a file, an HDF5 file. What we did is we called HDF5 dump, which is a program that dumps the data to standard out, and then we use a pipe to read in the data and put it into an array. Well, that brings me to the conclusions. I think D is very powerful for high-performance computing because it's a lot cleaner than C++. The code is small, it's fast. I think D code is as fast as C or C++ code. It has a lot of high-level constructs that you can use. So I can say we are still using D in our projects. I would say for acceptance of D in the broader HPC community, there are still several roadblocks. And the main thing is that there are not enough people in HPC, but in D in general. So there's a bootstrapping problem because there are not enough people using D. Another thing we certainly need to solve is binding to fundamental HPC libraries. It's not rocket science, but it's something that, well, at least I need to understand a bit better how to do this in an efficient way, right? How to do bindings to MPI, to BLAS, to HDF5. And then the third thing that we need to solve is like how to do distributed debugging. There are specific tools for distributed debugging and distributed profiling. And the main issue that I have there is that the D uses different mangling, and I couldn't get the demangler of D to cooperate with the profiling tools that we were using. So my goal for this D conference is to get a first idea in my head how we can solve these, especially the last 2 roadblocks, and how we can clean up this project that we have such that we do it we can do it the proper D way, and we can hopefully expose this D project to the broader HPC community. Thank you.
We've already got one question from Ricky on YouTube. Given that coroutines would offer compiler assistance with dependencies between tasks, are there any other language features that could help you? For example, reference counting for C++ classes or temporal safety?
I don't fully understand how coroutines would help in this context. We use coroutines in Go. We do a lot of, well, we like to do exploration of what languages to use for the problems, and we use Go a lot, and in that context we use coroutines. But for this specific programming model, I wouldn't know actually I wouldn't know how these different features would work. Again, I fail to see how the question relates to the system that we have here. Maybe when I think about it, I can see the connection. But
given that the problem you're trying to solve for is parallelism,
yes.
I don't think coroutines really bring anything for you, right?
Yeah, I agree. It might be able to allow you to use the resources, the cores more efficiently. You can schedule, let's say one task is waiting for data to arrive. That's a good moment to actually switch to a different coroutine. And in that sense, that's already what's happening. But that's again, mostly on this type of systems, the hardware takes care of making sure that, or the lower level libraries make sure that at a certain times you switch between tasks when you're waiting for data. So in that sense, we could use coroutines to be able to suspend tasks when they're waiting for data. Yeah.
Have you thought about posting a bounty? So I'll pay $1,000 or whatever the amount is to someone who will wrap it. I've had sort of implicitly good luck that way.
So
you need HDF5 wrapped. You need debindings to HDF5 for maybe a high-level interface.
I think it's a matter of doing it and then biting the bullet. I don't think there's a fundamental problem there. It's just a matter of finding what features of HDF5 we really want. Because usually the problem is that these the header files, C header files, they have macros in them. And finding out what macros you need and which one you do need and how you instantiate the macros to do the specific. Usually these macros, they say that this function exists for this type, but also for that type and this type, and I don't want to rewrite the code 20 times for 20 different types. I just say a macro, and then you say blah, 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 blah for all the types. So one way to solve this might be just like, okay, then I just run the preprocessor, generate this preprocessed header file once, and then I'm done, but maybe not. So there are probably tools. And so it's a matter of looking into doing it once and then never have to deal with it again. Of course, then the next version of the library comes around the corner and you have to redo it again because they changed the header file. So yeah.
You should talk to Attila, who wrote DPP.
Follow-up question to that discussion. Are you using ImportC to kind of automate the generation of wrappers?
I have been playing with it, but we started this project. We didn't. I don't know whether that already was part of. Does that feature work with the DMD compiler or also with the LDC compiler?
Both.
Both. So no, we haven't used it yet. I've played with it, but the code base started with people writing extern C declarations whenever we needed to. But it's something that I tried, and at first thing it seemed to work, and it seemed to work well.
An anecdote on that one: I did a CUDA.h using ImportC, and it went very well.
Okay.
And there's a technique that there's others here. Steve, you might talk to him. He has some experience with it too, and others. But one of the techniques you can use is to explicitly go to a .di file and then make possible manual adjustments at that point. And that will help keep you current as the things that you're porting evolve. You can catch everything. It externalizes. It's not a hidden pass anymore. You see it in the .di, and you get to play with it. So it's very nice.
Yeah, I looked at it, yes.
I think there was an adding of being able to qualify external C functions as well, just being added to the compiler last week, I think. Just a very good feature to have.
Thank you. Already getting lots of answers.
Yeah, it looks like we're out of questions here. So thank you, Tom.